Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a great pleasure to have Guy Lebanon with us. He came all the way from across the lake to join us today. Guy is a senior manager at Amazon, where he leads the machine learning science group. Prior to that, he was a tenured professor at the Georgia Institute of Technology and a scientist at Google and Yahoo. And even in his history, there is an internship at Microsoft. His main research area are machine learning and data science. He received his PhD from CMU and BA and MS from the Technion, the Israeli Institute of Technology. He has authored more than 60 refereed papers. He's an action editor of JMLR and was a program chair of CIKM and will be the conference chair of AI Stats in 2015, so be nice to him if you want your paper accepted. He received the NSF Career Award, the ICML Best Paper Runner-Up Awards in 2013, and the Dub Best Paper in 2014. He had the Yahoo Faculty Research and Engagement Award and is a CBOL scholar. So he's going to talk about the local low-rank matrix approximation.
Thank you very much. I wanted to say a few words first. This is work I did while I was at Google. And the collaborators, Yoram Singer and Sungyan Kim and Jun Sok Lee, are two of my PhD students at Georgia Tech. And they're still my PhD students, although I'll probably be handing them off soon and become a co-advisor instead of a regular advisor. I've been 1 year so far at Amazon. But we're doing follow-up work on this. And in fact, the follow-up work, like Ronnie mentioned, won an award at Dub. And I'm happy to take questions during the presentation. So please feel free to ask questions. And finally, thank you for hosting me. I think I know almost everyone here. And I'm happy to meet old friends. OK, so the matrix completion problem is this should be, or one way to describe it is as follows. We have a matrix. Let's think of it this way. And then we have some observations, some entries in the matrix marked by red are actually available to us. The numbers there are known. The black dots are unknown. And the task is to predict what's the value of the black dots from the red dots. That's matrix completion. So formally, we have these observations, a few entries of the matrix. And we want to predict the unobserved entries of the matrix. And this is very hard to do if we don't say anything else, because of course there's a lot of possible completions that are consistent with the training data, and how should we favor one over the other? In machine learning, we have this principle of trying to favor a simple model rather than a complicated model that agrees with the data to try to prevent overfitting. But what is a simple matrix? If it's a vector, we would probably put regularization on it, favor small entries, or sparse, favor sparsity. But for matrix, what does it mean? Probably the most popular approach to define what is a simple matrix or favor simpler matrices is to define that as the rank of the matrix. So we want to favor low-rank matrices. And the low-rank matrix, those of you that don't remember linear algebra, is a matrix that can be written as a product of two other matrices. One of them is tall and narrow. The other one is short and broad. And the dimensionality here and here is the rank of the matrix. And the idea is that that rank is much smaller than the minimum of this and that. Any questions so far? Okay. Okay, so how do we use that, or what's an application of this matrix completion problem? This is probably the most popular application these days, although there's other applications as well. Recommendation systems. Specifically, these entries are ratings. And here is how we interpret it. The row denotes the user, and the column denotes an item. And the entry denotes the number of stars given to that item by that user.
Is this really the best model for a recommendation system? Because a lot of, in recommendation systems, the values are not missing at random, and people, it's not truly Gaussianly distributed, and because that's sort of, there's an implicit Gaussian noise.
I haven't gotten to the loss function or the specific model yet, but you're right that in many cases this is assumed. And I can tell you, so this paper is an academic paper, and I've worked on it while I was at Google. But now at Amazon, I'm doing recommendation system in practice. And things are very different. So our RMSE performance does not correlate well to increases in revenue. It's not the same thing. And if you look at publications, and there's 10 papers, and one of them is the winner in RMSE, it's not necessarily the approach you want to take in industry in order to get better user engagement or better sales revenue increase or some other metric you're interested in. The whole concept, in fact, I would go further beyond what you said. The whole concept of offline evaluation is not working very well. We need to innovate how we evaluate not just a particular loss function, but the whole process of having a training set, training on a training set, and testing on a testing set. I don't think that's working well for real-world products. It doesn't get us beyond a certain point. That's a whole big topic. Okay, so anything else? Yeah, so the training data is some observations that we have. Think of Netflix example in your mind if you want. And the unobserved are the ratings of the users for unseen items. And if we can complete the matrix, we can recommend items to users based on these values. Now, again, I should say, this is not necessarily, if you want to build a recommendation system in industry, that may not be the best strategy, but that's the kind of data that we have in academia or public data sets. I cannot publish results on Amazon data sets. So this is results on, I'm going to show results on Netflix data sets, other public data sets, and that's the kind of things you can do with it. Yeah.
Is it a good abstraction? I mean, like these, like all these like data sets are kind of static. They like kind of they neglect time, right? And like the most pressing problem in recommendation is to predict what will happen like right now.
Yeah. Yeah.
So is it? Do you think it is worth like abstracting
Absolutely. So I don't want to talk about my work at Amazon, but I can just say very briefly, a lot of work needs to be devoted to thinking what do you usually watch in the evening or in the morning or in the weekend versus the week? Is it the kids watching or the wife watching or the husband? And is your taste changing? What about new movies that just came out? Everyone wants to watch them. There's a lot of subtleties. So I absolutely agree with you. This is kind of a well-contained talk within a standard kind of static offline data set. And I think still it has a lot of interesting ideas. So I don't think you'll be disappointed. But I agree with you that this is not necessarily the right setup for industry. Yeah, good point. Okay, so here is the standard or the most popular recommendation system if you look at academic papers. And if you think about industry, probably this is one of the main baselines or variations of this are still being used. Okay, so we have the thing to pay attention here is we have the observations, which we denote by M. That's the matrix of observations. And we take the squared error between the observed entries and the values of the reconstructed matrix. Then we sum over all observed entries. A denotes the set of training set. And then we find the matrix that minimizes the reconstruction error on the training set, subject to the rank of the matrix being a specific value. This is hard to optimize because this constraint is not very easy to work with. So what we do instead, we cast it in the following way, which is equivalence, the equivalent optimization problem. We optimize instead of over x, we write x as u times v transpose in that kind of factorized form that I've showed you earlier. And then we optimize over u and v. And there's no constraints, just a non-constrained optimization problem. If you want, you can add regularization, but this is much more convenient to work with. This is a very popular matrix completion method. It works reasonably well if you measure your performance by reconstruction error on test set. One issue is you need to know the rank R in advance. And another issue, it's not convex. And I want to say one more word about this, because if you remember linear algebra, SVD, there's a single SVD decomposition for any matrix. So why can't we find the right or the single SVD decomposition? The reason is that we sum here only over a subset. We don't sum over all entries in the matrix. If this sum was over the entire matrix, there would be a single SVD decomposition that minimizes the reconstruction error, and you can get that decomposition by looking at singular values and singular vectors of the matrix. But we don't sum over the entire matrix, and that introduces lots of local maxima. Questions? Okay. Now here is what happens if you run this kind of procedure. The y-axis is the mean squared error or root mean squared error on a test set. And the x-axis is the rank R of the decomposed matrix. And you get better test set performance, but as you increase the rank, but at some point you start hitting a law of diminishing returns. You can't increase the performance much further.
What are the units of RMSE? That's stars?
Yeah, that's right. That's right.
So there's no overfitting? I can increase the rank? Or does it go?
At some point there would be overfitting, and if you add regularization, you can probably do better. Yeah.
It goes to 0.95. What's 1? 1 is total ignorance, or?
No, so 1 would be an average error of 1 star away from the actual prediction on a 1 to 5 star. 1 to 5 stars, yeah.
Okay.
So it means an average error of 1, but it, in the sense of root mean squared error. More questions? Okay. So here is the observation. As the rank increases, the accuracy quickly hits law of diminishing returns. And let's consider the following two hypotheses. Okay? Hypothesis 1, the matrix that we are trying to complete has a low rank. And the law of diminishing returns reflect the best possible prediction. Okay? The data just has some noise in it. We cannot improve the prediction beyond that. We've correctly estimated the rank, and we're using the right rank. The second hypothesis is that the matrix that we're trying to complete has a high rank. So the low rank assumption is incorrect. And in this case, the diminishing returns, I mean, why doesn't it keep improving if the matrix has low rank? The diminishing returns are due to overfitting. And the reason of overfitting, because as you increase the rank, you're going to have more parameters. The matrices that you use, the factorized form, have more and more parameters. And you would overfit because the data doesn't grow. You can't grow it to infinity as you increase the rank. The second reason could be convergence to a poor local maximum. And yeah.
So how do you formalize the fact that it's either low or high? It seems like a binary distinction, while in reality there's going to be a sliding scale of as you increase the rank, you're able to fit better, but at the same time there is like overfitting possibility. Is there a clear way to say like there's a knee in some metric which indicates
so this assumption is on the original matrix,
right,
that we don't observe fully, and this has either a low rank or a high rank.
So you're saying that you always pre-assume that there is a fixed rank that
we assume there is a truth. We assume there is some matrix that we're trying to complete.
Right.
We don't know what it is precisely, but it exists, and it is either has a low rank or a high rank.
But you're not viewing it as a probabilistic assumption that basically there's some distribution over possible ranks that
No, it's either
or an eigenspectrum
or an approximate rank.
Yeah, approximate rank.
yeah. Okay, so what I'm going to try and argue with this presentation is that in the context of recommendation systems and standard data sets like Netflix and other data sets, the second hypothesis is the correct one, rather than the first. But also, the first hypothesis is incorrect globally, but is correct locally, and I'll explain what that means. The third thing is combining SVD with non-parametric smoothing significantly postpones the diminishing returns, and it also reduces the computation. So we have a win-win situation here. And in fact, the computation is a big problem because data sets are big in industry, and in many cases we're having a real computation challenge trying to optimize that function that I showed before. Okay, so I'm going to describe the model first informally, and then there'll be a formal definition later. Okay, so this is the informal description. A matrix complete. So here is the assumption. Okay, we're assuming two things. We're assuming that the matrix completion that is accurate across all users and items should be of high rank. Second assumption is a matrix completion that is accurate for one specific type of users and one specific type of items. For example, if we only look at the population of teenagers and we only look at the population of old movies, that kind of submatrix, teenagers and old movies, will have a low rank. And the low rank is probably teenagers don't like old movies. The rank is 0. Right? So it's like a very simple problem. Once you narrow down your problem to a very coherent population of users and a very coherent population of movies. The problem comes because you have a lot of these coherent subpopulations, and if you want a matrix that is correct globally, then the rank will be high.
So
yeah.
The low rank block is not where to state that.
Sorry?
That the matrix M is composed of low rank blocks.
It's not, so it's more complicated than that because these populations may be overlapping, and it's not necessarily a block structure. But that is a correct intuition. Okay, so here is the algorithm. Okay, identify Q neighborhoods in the set of matrix entries. So first thing, please parse the sentence here. Okay, we have a set of all possible matrix entries. Okay, this is a set, but we can also think of it as a space with a metric structure that is discrete. It's a discrete space, not continuous, but we can still say it's a metric space. And we can still define the notion of neighborhoods if we have an appropriate distance function. How do we get that distance function? I can talk about it a little bit later if you're interested. For now, let's just assume we have a distance function that measures similarity of items and similarity of users. Let's assume this is given. If we have that measure, we can identify the neighborhoods.
So you're assuming metadata.
Yeah.
Not necessarily, actually. In the experiments that I'll show, we get the neighborhoods from the training set that we use to construct the matrix factorization later on. So we don't use additional data. We use the same data to construct the neighborhoods as well.
Are you using the neighborhoods because that particular subset will result in a low rank approximation for that piece, or is that we're using a different criteria to try to find the subsets here?
This is a pretty big issue, how to find the neighborhoods. In the work that we've done here, we're using a pretty elementary technique, and I can discuss how we do that.
But is it a kind of latent variable of the problem, or is it something like there are neighborhoods that are given to me by an oracle by any
Right. So
technique, or they are
okay. So
optimized?
I'm happy to describe. So what we did to define the neighborhoods, I prefer not to get into that right now, but I'm happy to answer since both of you are interested. What we did is we sampled entries from the training set. Okay, we sampled entries from the training set, and then we define neighborhoods that are centered at these sample. So say we sampled 10, for example, we want to have 10 neighborhoods. We sample 10 entries from the training set of entries, and then we form 10 balls in the distance metric that we define, centered around these 10 samples. We have a follow-up paper where we do this in a more adaptive manner. Yeah.
Just to be absolutely clear, the neighborhoods are not necessarily block matrices, right? It could be all over the...
Exactly. Yes, absolutely. Absolutely. And in fact, they don't even have to have, it's not like they have to be block. Even if you permute the rows and the columns, you can still not get blocks. But absolutely, yeah.
So meaning the neighborhoods don't have that kind of structure?
Not necessarily in the general situation. I mean, we are using a distance metric in the a product distance in the experiment, but not necessarily. Okay, so we identify these Q neighborhoods, and the way we do that is we just sample Q points from the training set observations, entries, and we create balls around these points. And then for each of the neighborhoods, we construct a separate low-rank matrix that is especially accurate within it. We don't care so much about being accurate outside of it. And then we patch up these local models to get a matrix approximation that is global and that is high rank. But the local patches are low rank.
But you're doing no refinement of the neighborhood to improve the fit of the low rank at that point. Like the neighborhood's fixed.
That's right.
Point.
That's
Okay.
right. Like I said, we have a journal paper where we generalize this. But right now, we just identify the neighborhoods. Right now, in a very naive way, we compute a local model and then we patch up the local models. Okay, so here is a picture of the neighborhoods. But like Chris said, and I always say this caveat, this neighborhood isn't normally adjacent rows and adjacent columns. Okay, because for example, this movie may be similar to this movie and to this movie. And this user may be similar to that user. But I cannot visualize it in a different way. So this is just for the sake of visualization, assuming that the distance function just is the distance between the indices. Okay, so these two are necessarily similar items. These two a little bit further, same thing with the rows. You could get something like this kind of neighborhood structure. That's one thing I want to mention. The second thing I want to mention is not exactly what we do. We do something a little bit different because here we assume the neighborhoods are precisely defined and they have a precise boundary, and everything within the neighborhood counts in the same way. We use something called kernel smoothing, where there's a weighting function that gives the weight corresponding to the distance from the center of the neighborhood. And that means we can have neighborhoods that cover the entire matrix even, or cover a subset of the matrix. But as you get closer and closer to the center, that weight becomes higher.
So just to make sure that I understand, so at the end of the day, what you're getting are basically the model can be represented by a set of centroids and a set of matrix completions which were trained to be local.
That's right.
So when you want to do a prediction, how would the prediction work?
So I haven't gotten to this. I say patch up, that's the first step, the third step. I haven't gotten to it yet. I will show you in the next slide or two how we do that. Yeah. I think you're next.
So if, let's set aside the low rank stuff. If you have a distance metric already defined, you can define a Gaussian process if there were constants and just make predictions. So what you're saying is that you could always if you have a distance metric or a kernel on your sort of item movie pairs, you can always just do Gaussian process regression, right? So it's what you're doing, and that's kind of like you can imagine a Gaussian, I mean this is weird because it's in this funny space, but a Gaussian with different size bumps that are positive and negative and trying to predict. Now are you doing, there used to be an old technique where you took the Gaussians and then had like a little local linear model that sort of turned on by each Gaussian. Is that what you're doing?
HME kind of stuff?
A little bit like HME, but it also goes back to Anders Crow and that old saying.
I think it would be similar because that would correspond to a low rank structure, right? Like a local low rank structure. So I think it's similar. Not exactly, but there's some relationship.
Okay.
Yeah.
So I don't know if you've also tested versus just the plain old Gaussian process where you take your neighborhoods and just have constant. Everything is ranked 0. I don't know if you tested that.
That performs very bad.
Oh, okay.
Yeah. The local low rank is crucial because it kind of discovers this like local semantics structure in it. I'll show you later graphs where you can see the performance of the local model as a function of the rank of the local models. And you can see that we really postpone the law of diminishing returns, and there is indeed a significant improvement as you increase the rank of the local model. Okay, so here is so this is the first step, identify the neighborhoods. Okay, second step is for each neighborhood construct a local low rank matrix completion. Suppose we look at this neighborhood and remember we have this weighting function. So we want to get this low rank matrix that approximates the entire big matrix, but it especially is accurate here. And a little bit less accurate here, a little bit less accurate here, and here we don't care. And that will be the local model that correctly describes the situation here. If we want to think of it intuitively, we can think of teenagers and old movies. But like you said, we can do that even without metadata, just by figuring out which users have similar viewing patterns and which items have similar viewing patterns. Yeah?
You only did that. The neighborhood would be always rectangular, and you certainly are not.
Depends. Yeah, I mean, in the experiments we did use a product structure. This is, like I said, the neighborhood will not be kind of spatially similar to each other, but in our experiments, the neighborhoods do have a product structure, but you can think of whatever distance you want more generally. If you have metadata, you can use the metadata, and conceivably one would want to use non-product distances. Okay, and then the third step, once you have these local models, you have a local model for here, and for here, you would patch them up. Okay, so we are ready for the formal description, I think. So here are what we have. So we have a distance function on the set of matrix entries. And this is, in our case, computed based on observed matrix entries. But it could also be computed based on additional data, like if we know the directors of the movies or the actors or the genres or whatever, or we know something about users, we can have that help us. Okay, and here is what we assume to be the truth that we're trying to discover. We assume that there is an operator that maps the set of matrix entries to matrices. So for each matrix entry, we get a specific matrix. Okay? This is the set of all matrices, and these are the matrix entries. So for each matrix entry, for example, the entry row 2 and column 3, we would get a brand new matrix corresponding to that. And that matrix has two properties. One property, it has rank R, low rank. The second property is that that matrix evaluated at the specific matrix entry that we picked here would give us the same as the observed value. The second property of the operator is that it's somewhat continuous in just a second. It's continuous in a sense that it's slowly changing, because we don't want the operator to jump wildly. The whole point in defining the distance function is that the distance function means something. What it means is that that operator, if it maps 2 points that are close to each other, it will give us similar matrices. Now, this is not a continuous space, so slowly varying or smoothness we define in this way, which is called Holder continuous. The distance between, this is one matrix evaluated, this is the operator evaluated at one point, the operator evaluated at another point. These are two matrices. The Frobenius norm between them is less than the distance between the two matrix entries. And we have to have that inequality, meaning it cannot change too much. Wait with your question because I have a diagram that may make it more clear, and then I'll take questions. Here is a picture of what we have. So this is the matrix that we're working with, okay? And each point in it is mapped to another matrix by this operator. Okay, and these matrices all have low rank. And as we move from one point here to a neighboring point, neighboring defined by the distance that we defined, if we move a little bit here, these matrices should move also slowly, should not change too much. And the value of this matrix here is the same as the value here. Okay? And the value of this one here is the same as the value here. So these matrices have to agree with the values in this matrix. That's one. Second thing, they have to have a low rank, these ones. And the third thing is they have to change slowly. Yeah.
So we've gone from matrices defined for neighborhoods to essentially matrices defined for central.
For every single matrix entry, we have a brand new matrix. Yes. And this is not something we have to find, but this is the model, what we assume is happening. We have these matrices. Now, these are low rank, okay? And they describe what's going on in this point, and they change slowly.
This slow changing property you're only requiring within a neighborhood, right? Not across neighborhoods.
No, it's defined. It's defined this way.
Okay.
Yeah.
I see.
So you have to have D is a kind of global.
Yeah.
so all your
D is the
neighbors have to
distance
kind of use a
measure
compatible
here.
distance.
Yeah. That's,
So yeah, D is the distance measure here that we define. It's up to us to define. If we do a bad job with defining D, then obviously this assumption will not be correct.
but to evaluate T,
Constants will be large.
but to look at T across, because your different patches will have different range sizes, right?
Yeah.
Like, because your different neighborhoods are different sizes. So T for one is not the same size as T for another. Or is this a global T?
So T, the size of T maps them to the same size. All of them are matrices over the entire set.
Entire space.
Yeah.
Okay, I see.
So these are the number of users and number of items.
So will your exponent beta depending on the dimensions, like N1 and N2 sizes?
Probably. Yeah.
So two questions. One is the rank is fixed across the entire index space?
Yeah, this is also something that can be generalized, but in our experiments we use a single constant R for the rank of all of these matrices.
And the second question is the distance metric is not on neighborhoods but on pairs.
That's right. That's right. Yeah.
So have you thought about bridging this? Because right now D is completely separate, right? So ideally you would want to sort of vector off and learn a good D that would give you good partitioning, good smoothness, and so on, as opposed to trying to fit some D that may or not be the right one.
Yeah, yeah. Yeah, that's a good point. I mean, we haven't done any work on that. Our first extension was to, I haven't even showed you what we're doing formally, so I want to talk about it very quickly. The first extension is to work with ranked loss functions, which performs better in real world cases than squared loss. Second extension was to work with, to try to identify the neighborhoods in an adaptive manner. And what you're talking is another level, which is adaptively modify D. Which, yeah, that's another reasonable approach.
So you could do it either by defining D or by partitioning.
Right. So right now in this work we assume D, and if you want, I'll tell you how we get D, but we get it from the training observations based on similarities between what users view and how items are being viewed. Okay, so this is another. I'm just going to skip that, I think, because I don't have that much time. So here is, we have two estimators. Now I need to show you what exactly we do. I haven't yet showed you formally. There are two estimators. One is called the expensive estimator. And this estimates the operator, T, okay? So we're going to estimate we're going to estimate each one of these matrices, okay? And each one of these, if we estimate the matrix, this one, we can evaluate it here. And this can serve as an estimate for this, okay? So we're going to do that for every single point. And that's why we're going to call it the expensive estimator. And then we're going to have a cheap estimator that I'll show you how we do. Yeah.
Before we jump in, how many neighbors are you talking about? About 5 million? What sort of numbers are in your head?
I think I show you a graph. I think I may have a graph as a function of the number of models, but I would say in the tens or in the hundreds, I would say. Depends on the size of your matrix also. So this is the expensive estimator. So here is what we formally do, how we get our model. We look at the training set and we learn a low rank matrix that minimizes the squared reconstruction error, but we give weights. The weights correspond to the distance of the point from the center of the neighborhood. Okay? So because I want my local model to be particularly accurate in the area, in the neighborhood that I'm choosing, so I want it more and more accurate as I get closer to the center, subject to a low rank. So I showed you already how to do that without the weight. I showed you earlier how we do without the weight. Sticking in the weight is relatively simple. It's same difficulty level. And then I just evaluate this estimate that I've computed at the point I want to predict, and I get my matrix of completion or approximation. K is a kernel function defined in one of these ways or a different way, just something that measures is higher and higher as you get closer to the center. And what's the difficulty here? Difficulty is that for each entry that we want to predict, we have to do a separate SVD. We have to run a separate SVD. When we need to estimate a rating for a user, for a movie by a user, we sometimes get it at runtime. We don't want to solve an SVD at runtime and have the user wait for the answer. And even if it was offline, it's still too much to compute. So this is not practical. And we're going to get to the cheap estimator, which is T double hat. And this is going to be very practical, actually. In fact, it's going to be so practical that it's going to be faster to compute than the non-local version. So here is the cheap estimator. First step is compute the approximation T hat at Q anchor points, S1 through SQ offline. These are what I said, the neighborhoods that we identify. And the way we construct them is we just sample the centroids from the training set, and we put a certain ball around them. OK, so we compute Q local models. Okay, we compute a low-rank model that is especially accurate as you get closer to these centroids. And then you patch up these local models, these Q local models. And how do you do that? So you have different values you want to patch up. We do that using a technique called kernel regression. This formula specifically is called Nadaraya-Watson local regression or kernel regression, locally constant kernel regression. And the thing we do here, though, this is kernel regression in the space of matrices, as opposed to standard way of talking about kernel regression is you say kernel regression on a real line. But here, instead of points, scalars, doing kernel regression over scalars or over vectors, we do it over matrices. So in essence, this is just an average, weighted average of the local models. And the weights are reflected by the similarity of the local model to the point that you want to predict. And then you can form your completion this way. So what do we have here? We have step one, offline computation. You can do that offline before you need to serve anything to users. solving k low-rank SVD problems in parallel. Step 2 is this patching up could be done very fast. Linear combination of local models. We're going to show you some graphs soon that shows improved prediction accuracy as well as reduced computational cost. Now, why would you have reduced computational cost? Because you replace one SVD with Q SVDs. So how do we save computation? Any ideas? Okay. That's right. So there's two ways that you gain. One is because the kernels may have a finite support, and then that means you can solve a smaller matrix approximation or low-rank SVD, and it could be much smaller. That's one gain. The second gain is that the rank of the local models can be much smaller than the rank of the global model that you do alternatively. And solving, say, 100 SVDs of rank 50 is much easier than solving one SVD of rank 5,000.
If they're truly complex at work, and they actually go to 0, though, then you need to check to make sure there aren't places in the matrix where you have all zeros from everything.
That's right. That's right.
Nothing.
That's right. So you have to be careful there. But there's these two gains. One is the support, and the other one is you can get really good results by having a really low rank, much lower rank than the original low rank for the entire matrix. And it's easier to solve many problems with low rank than one problem with bigger rank. Yeah.
But SVDs are mainly like a recommendation system online SVD, not SVD, right?
So I mean this problem right here. I call this incomplete SVD because we sum only over a training set. We don't sum over all the entries, which would be the algebraic SVD. Right. So this requires gradient descent. You cannot do singular values, singular vectors. Okay. Let's show you some results. So the x-axis is the number of anchor points, which is the number of local models or centroids or patches. The y-axis is the RMSE on test set. These dashed lines show the performance of SVD, which is the standard baseline, still very popular. As you increase the rank from 5 to 7 to 10 to 15, you see law of diminishing returns. Right? Very quickly, you get to a point that you cannot improve beyond. And the reason you cannot improve beyond is what we said earlier, that issue of overfitting and convergence to a local maxima. The local models, the performance increases as the number of anchor points increase. And they also increase they also get better as you increase the rank of the local model. This is rank 5. Every local model is of rank 5 here. Okay? But we have 45 models of rank 5 each. Okay? So the total rank will be 45 times 5. Okay? The rank of the big matrix that we approximate will be 45 times 5. Here it will be 45 times 15. But you see that if you would keep increasing it, you're basically going to be stuck here if you just do a rank 500 SVD. It's not going to get much better. Sorry?
What's DFC?
DFC is something called divide and conquer matrix factorization, a paper by Michael Jordan, Lester McKay, which does a similar trick of dividing the original matrix into patches and learning local models and then patching together. So it's a relatively recent paper that takes a similar approach. And this is the Netflix winner. Although it's a long story, we used slightly different data set than the Netflix winner. So this line should be it's the same size, but this line should be taken with a grain of salt. It's not a formal comparison.
Do you know where the limit is? I mean, because you're showing up to 15, but then what?
Yeah,
does it get to keep getting better?
Yeah. So right. So you start hitting the limit pretty soon after.
Oh, really? Okay.
So when you're all the way on the left, right, if you have, say, one anchor point, you're still not doing the global because
That's
of the
right.
weighting, and
That's right.
why
That's right. So that's a very good observation, actually. Look how better we do with even a rank 1 with one anchor point. Why do we do so much better than the global SVD? Because we sample the anchor point from the training set, and the learned model is more accurate in the vicinity of the training set than in remote corners of the matrix that you don't care about. So we particularly focus our attention on what we've seen in the training set, which is a good proxy for what we're going to see in the test set.
So how does the training RMC looks like? So what you said is that basically you can refactor the model which uses, say, 10 anchor points into a single matrix of higher dimension. So does it indeed have, how does its training, so if you want to show that it's a problem of the optimization, you want to compare the training error, not the test error.
It's not a problem of the optimization, it's a problem of the generalization or the learned model on test set.
So in terms of its train error, actually its train error is going to be worse than the train error of if I would have done a model, SVD model with a appropriate trend.
No, I think the training error would also probably be better, but the real comparison is, I mean, you really care more about the test error, I think.
It's true, but if we try to understand what is the source, what is the bottleneck, then it's interesting to look whether it's just a better optimization method. So it's better off if I have so in a sense it would say if I have a large non-convex.
Okay, I see what you're saying. So you're saying how much of the problem is convergence to local maxima? That's what you're saying. And it's difficult for me to say because the search space is so big and there's a lot of local maxima. It's difficult to do an exhaustive search and say with certainty, here is the global maxima. But that's a good point. Maybe we can look at this further to kind of quantify different. I just have a few more slides and almost out of time. So
do you have
quickly
an
though.
evaluation where you show the non-approximate one, where you center at your query point? Let's say I give you the query point, like there's only 5 of them, so it's actually cheaper than doing Q of them, right?
Yeah, so we have that comparison in the follow-up paper, journal paper, because there we adaptively select the anchor points, the centroids. Yeah. Let me move ahead because there's a couple more things I want to say, and we're almost out of time. This is not something that we did, but I think is interesting a couple of slides that I think are interesting to learn about, and then something that we did. But it's all related to this, right? So the nuclear norm of a matrix is the sum of the singular values. This is the definition. And that's another way of defining simplicity of a matrix. Remember I said simplicity is the rank of the matrix. This is one way to define simplicity. An alternative way is perhaps the nuclear norm. So we want to favor matrices with low nuclear norm. One of the motivation is that minimizing the nuclear norm subject to some constraints is a good surrogate for minimizing the rank of the matrix. Just in the same way that minimizing the L1 norm is a good surrogate for minimizing the L0 norm. There's papers showing both results. So there's some kind of parallelism between these two problems. So that kind of leads us to the following matrix completion problem. Given a data set, you minimize the nuclear norm of all possible matrices subject to the matrix being not too wrong on the training data. That's an alternative matrix approximation or matrix completion problem. And it has gotten a lot of attention recently in academic community. Industry, not so much, but I can say why, but lots of papers in academic community. And I think in large part because of this, and it has some compressed sensing properties, etc. So we thought maybe we can do a local version of that as well. And here is the local version. Minimize the nuclear. So the estimate of the operator at a particular point would be the minimization of the nuclear norm of the matrix over all possible matrices, subject to reconstruction error not too large, where reconstruction error is the same, except we have these weights, kernel weights, to tell us how much we care about different reconstructions. So in general, this has an advantage in that it's a convex problem. And there's a single global maximum. It has an advantage that you don't need to specify the rank in advance. However, you need to specify alpha. Okay, so you don't quite get away with that.
So it's weird, right? Because MCD and AB goes over all the. CD also goes over all the observed points. So you're kind of reweighting the MSE for each of the points or something? Or?
So this would be the training set.
Oh,
so
the local.
Yeah,
this
so this is a local at one specific point. This will be the cheap estimator.
I see.
And we have to patch up multiple with local regression. We will patch them up to get an estimation everywhere, wherever we want. We will patch them up.
Okay.
One difficulty is that this is harder to compute in large scale because this requires a semi-definite programming optimization. And for large scale problems that we have in industry, this is not very practical. Okay, so there's this. Do I have another 5 minutes or? Okay, so there's this really interesting result by Donohoe and Tao and some other people, and it goes like this. And I think it's really interesting to be aware of that. Completion of a rank R matrix is possible with high probability if the number of observed entries satisfies this inequality. So n is the minimum of n1 and n2. And for simplicity, let's just think about square matrices, completing square matrices. So the number of observed entries needs to be larger than n log n times r. Only log n is to the power of 6. And r is the rank of the original matrix. So if we fix the rank, we need the number of observed entries to grow at the rate of n log n, almost n log n, and n times log n to the power 6. And I'm sorry?
What kind of value is the C1?
I don't know. Yeah, I'm not sure. The even more interesting direction is that if this is not true, okay, then it's impossible to reconstruct the matrix. If this is not true without the 6th power. Okay, so we have like kind of exactly the rate at which with which n needs to grow, or number of observed entries needs to grow. So if you don't have the 6th power, this is the lower bound. You cannot succeed if the number, for any algorithm whatsoever, similar to the result in compression. You cannot compress better than the entropy rate with any algorithm whatsoever. Just the same. So same thing here. So this is the first interesting result. The second result is that this method that I showed, this thing right here, actually works with this rate. So there's some error rates, but it basically shows that the method that I showed you in a slide before achieves almost the lower bound. It's almost like the best optimal compression, the best optimal reconstruction, except that you need the 6th power here. So we almost accomplished that optimal rate. And the way this relates to the talk I just gave is that we've kind of generalized these results to the local variation. So we get kind of bounds on the reconstruction error that is similar to what they got in that paper. I think I'm out of time, so let's just talk a little bit about next steps. Matrix completion with nuclear norm minimization, extend framework to rank loss function, adaptive selection of anchor points, large-scale massively parallel implementation. We've actually done all of these, but there's other future steps. Maybe I haven't told you how to get the distance function. I can tell you what we did here. What we did is we did an initial SVD, global SVD, and then we looked in the latent space what is the distance between the users and the distance between the items, and that gave us the distance that we used in our experiments. I'm happy to answer more questions, but if you guys need to go, I think I'm out of time, so I just want to make sure.
Thank the speaker. And
thank you.
So the result
the lower bound. Isn't it something like you have to also have that the matrix has to be incoherent, like the singular vectors have to be aligned with it?
There are some conditions for that. Yeah, that's true. There are some conditions that I didn't represent. Yeah.
Yeah, I'm curious about how important it is to put this all back into one big matrix. So let me propose a naive algorithm and tell me where this would fail. Let's imagine we had some way of, pick 50 or 100 anchor points randomly. And then let's imagine we have a way of sort of clustering the users of the movies into those 50 different clusters based on those anchor points. And now for each of these groups, just do a low rank matrix approximation. And then when you need to make a prediction, you just use the membership weight. It could be soft clustering. You use the membership weight to the clusters. Each of these low-ranked matrices, which would be fast and easy to do, just makes its own prediction. You combine the prediction with those weights. Where would that fail?
So this is actually, I think it would succeed. This is very similar to what we're doing. There's only a couple of small differences.
Right.
One difference is we use instead of partitioning into separate problems and each problem being matrix SVD, matrix approximation, we make it a weighted matrix approximation so that it's increasingly more accurate as you get close to the centroid, rather than just have everyone have equal weight. So that's one difference. The other difference is how exactly you take the linear combination. So the details matter. Some formula would work better than others. I don't know exactly what's the best way. The formula I just gave is locally constant regression. Conceivably, there are other better ways of doing it and worse ways of doing them. But it's very similar to what you described.
I have a question about the setup. So let's look, for example, at search, right? So I can look at it as if I have the matrix of queries versus URLs. And I know, say, I have partial observation. Say I know from click data or from whatever other source on some pairs, I know the rating. So would it be a useful approach to try this kind of matrix factorization, or at all this kind of approach of recommendation system toward this problem?
Yeah. Actually, we were thinking about looking at other data sets like document term matrices, or in social network you can think of graph structure. So we actually thought about doing that. We haven't yet, don't have any experiments to result, but any experiments to report, but I think it's an interesting possibility.
So how would you think it will compare to more kind of the more prediction approach that?
Yeah, my estimate, or my guess, is that it would work also well compared to, say, LSA, or for example, in social graphs, you have a problem of predicting links. You want to recommend links. Hey, maybe you know this guy. My guess is that it will work equally well. It will show an improvement because the assumption that there is a global low rank is incorrect. And if you just try to increase that low rank, you're going to start facing overfitting problems. So assuming local low rank is an effective way of defeating that problem. So I haven't tried it also. That's just a guess. Yeah.
So your work mixes kind of two things. It mixes this kind of high rank as a sum of low rank, and then solving like local low rank problem. And they could be decoupled, right? You could have a parameterization, which is like a weighted. So let's say your score is a weighted sum of dot product of a few q latent vectors, and then you could perfectly optimize the global MSE with that. So is it important to basically solve this introduce extra regularization, right? To solve local problems.
So I think it's very useful from a computational standpoint to separate the problem into several smaller problems. We also looked at that. So we looked at solving the problem while optimizing overall, learning all local models at the same time, not separately. But computationally, that could be difficult.
This is difficult, but is it a good regularizer? So there's like the computational aspect and there's like the modeling aspect. Is this constraint of I have to solve the local problem good for modeling? Or?
I think it works for us. We haven't noticed the problem that yeah, we didn't find the other approach to work better.
I see.
How sensitive is it to the distance, and how easy is it to get gains by improving the distance?
It's actually very sensitive to the distance. If you pick a bad distance, and all of this is worthless. It's not sensitive in the sense that if you perturb the distance a little bit, it's going to perform poorly. But if you pick a bad distance, then there's no point. The first attempt we had was using the distance just be the relationship between the observed row indices and the observed column indices without doing a first SVD and looking at the latent space. That did not work as well because of a problem of sparsity. Two users oftentimes they have completely disjoint movies that they've watched. You don't know how to compute the distance between them if you look at the original space. So that did not work well. The distance that we used then, which was the most obvious one, just look at the cosine similarity of the observation vectors, didn't work well. When we did it in the latent space, that worked much better. So I think it's very important, but it's not sensitive in the rigorous mathematical sense.
And then how about adding metadata or other things to the distance? Does that further improve the results that you...
We haven't tested that, but we hypothesize that it would be very helpful, especially for items that don't have a lot of viewing history, or for users that don't have a lot of viewing history. You get a very poor notion for distance. If you have, we call the cold start users and cold start items. So for these, I think metadata would be very crucial. Yeah.
I'm curious if you or anyone else, because MSE is such a weird metric for this. As you were saying earlier, it's kind of like getting the average. Like there's a lot of threes. Who cares? For instance, you could imagine saying that let me look at all the fives and all the ones, and look at accuracy of getting the love-its or hate-its, right? And that might be more meaningful. I should never show the hate-its, and I should always show the love-its or something like that.
Yeah.
Are there have people tried any metrics like that?
I think the main alternative, which I do think is an improvement, although I don't think it's necessarily good.
Okay.
Like I said, it's still poor substitute for what you want to do in the real world. But the alternative is to use ranked measures, because the thinking is what you care about is you show to the user 5 movies or a carousel of movies, and you care about being accurate in the top 5 or top 10. You don't care about the rest of the 50,000 movies. So that's a reasonable improvement. Actually, I think quite reasonable.
The once it gets down to the weeds, like once you're in the 2, 3, 4s, it might not really matter, right? Like the differences the users make between like 3 and 2.
That's right. That's right.
Yeah.
Like the CG, right?
Yeah.
So
exactly.
one of our extension, in fact, the paper that won the award in exactly generalized this to the ranked loss approach, where we both trained and tested, evaluated based on the ranked loss measure. Yeah.
Things like you had features for the users and the movies. You wouldn't need to do all this stuff because the features themselves would give you a metric, and then you had a bilinear model where you combine the users with the user matrix and the features with the feature matrix. Then you would get like automatically this something similar to your operator.
So I think one has to be a little bit careful, and also I would say humble. What you said, I think, would work well or would work better for movies and items that we don't have a lot of viewing history for. But if we have a user that have watched a lot or rated a lot and a movie that has been around, I think these methods would perform better than methods with features. No, than feature-based methods. So it depends really. I think there isn't like feature-based is better than collaborative filtering. I would say it depends on which users and on which items. In some cases, you're right, this would work better. In other cases, the collaborative filtering approach is the one to use actually. And we've had confirmation of that also in experiments. And also, of course, depends on the quality of features. Like, what do you know about your users? Like, maybe you know their names and address, that's okay, but do you know their browsing behavior or which ads they clicked on? I mean, the more you know, the better.
In music, that's definitely true, because like if you use feature-based things, like you get all kinds of really crappy music with the right descriptors or something, but it's not good music. Whereas the metadata, or sorry, the count data actually tells you something really meaningful about whether people like it.
So I really think you have to look at both approaches. Okay, thank you very much.
Thank you.